Okay, so today I'm looking at the Z-turn board from MYIR, a company in China. MYIR standing for Make Your Ideas Real. Okay, so this board, if we go around, just take a look at what's on it. First of all, this is the Zinc 7010 version of the board. It costs $100 or $99. Then there is also another version of the board with this 7020 on it. And the price of that one, I think, is $119. Okay, so what we got on this board, we got gigabit Ethernet here. We have some jumpers here for selecting the configuration mode. We got push buttons here, reset push button for reconfiguring the FPGA, and a user push button here that you can use in your applications. We have a buzzer here, that's pretty unique. I haven't seen that on many SOMs. Have a CAN interface again, that's something I haven't seen much. So, and then over here you've got a USB port. They're mini, both of these are mini USB connectors. This one here is a USB UART, so that one we'll use that one today. You have an SD card and SD slot. Here you have a JTAG connector. I don't really like that JTAG connector. That's one of the things I don't like about this board, is that they've used a JTAG, they've used a header, a pin header that's I think 100mm pitch, and it's just not the right pitch for my JTAG programmer. As you can see, that won't go on there. Now, most Xilinx evaluation boards don't use this. I think this is very old. On the very old boards they used to use this, but now I don't think this is used very much. So yeah, that's one of the things I don't like about that board. I'm forced to do my work through the SD card. So if I want to do the designs that I do today, I'm going to do them by booting off the SD card, unfortunately. Now over here you've got a tricolor LED, so that's for if you need a LED. Now you've got some other LEDs here. I think you've got FPGA done in there somewhere, power good probably. Over here you have an accelerometer, so that's pretty cool for applications where I guess you've got movement, so you want to keep track of the orientation of the board, or detect movement of the board, that kind of stuff. You can play around with the accelerometer for that. You have over here a 5-volt jack to power the board. Now the board comes with an adapter, so a 5-volt power supply that you can plug into the wall if you want to power it through that. Alternatively, you can power it through the USB connector here from the computer. That's what we'll do today. I find that pretty handy. Then over here, the last thing, it's what differentiates this board, I think anyway, from the other SOMs, the other Zinc SOMs that are on the market, or let's say single board computers that are on the market. It has a HDMI connector on it, so you can say run Linux on this thing and connect the thing to a monitor, so you can have you know, a full GUI if you want, and run Linux. So yeah, I think this is a pretty unique board. I don't like the JTAG connector, but that's a little issue. So let's today in this video, what I'm going to do is build up a simple example design in Vivado. Then we're going to take that example design into the SDK, and we're going to test it out on. We're going to test the hardware out on the running the Hello World example design, and then after that we'll try out the Echo server running lightweight IP, and we'll test out this gigabit Ethernet. Okay, so let's get started. Okay, so to get our Vivado project going, the first thing we need are the board files for the Z-turn board. Unfortunately, you won't find them on the website, or I didn't find them anyway, but you will find them on this GitHub repository, Q3K Z-turn stuff. So I'll leave the link in the notes at the bottom of this video. So what you want to do first of all is click here on clone or download zip So I'll click on that and I'll just click open. You go through those files there. So Z-turn stuff master, then into boards, board files. Then you click on the specific Z-turn that you have depending on the device on it. So I've got the Z-turn 7010, so I highlight that. Then I copy that. So you need to copy that. Then you need to paste those files into your Vivado installation. So your Vivado installation is probably somewhere like this: Xilinx Vivado 2017.3 data boards board files. So you go into that folder and then you paste that folder we just copied a second ago. You can see here that I've already done it. So once you've copied the board files into the Xilinx Vivado installation, then you should be able to create a new project in Vivado and actually see the Z-turn board show up in the list of boards. So let's do that. Create a project. I'm going to call it Z-turn base. It's an RTL project and I don't specify sources at this time. Instead of selecting a part, I select the board, and as I said, we should now see the Z-turn listed in that list of boards. So we've got Z-turn. Here we click on Z-turn. Next, finish. Now that'll create a project for me using the part that's on the Z-turn board, and it will have all the information regarding how the zinc is wired up to devices on that specific board. So now the first thing we want to do is create a block design. Now we want to click the plus sign and add the zinc processing system to it. So when I do that, now I've got the option here to run a block automation. Now that's because I've created this project with the board files. So I want to use that. So now Vivado is going to use the board preset and configure the processing system as it should be for the hardware that's on the Z-turn. So I click OK. I can see that the board preset has enabled 2 of the fabric clocks. I don't know what they are, so I'm going to click and just check out the configuration myself. So if I double click on there, I open the configuration, I can see everything that's been configured. So I'm going to start off with the clocks. Click on clock configuration and check out the fabric clock. So we got PL fabric clocks enables F clock 0 and F clock 1. F clock 0 is 100 megahertz and F clock 1 is 50 megahertz. So in this design, I'm just going to run everything off this 100 megahertz. Off F clock 0, I'll just run it all off 100 megahertz, but we don't have anything to put in the PL, so at the same time doesn't really matter. So now I'll go into the zinc block design and check out what has been configured. So over here I could see my list of IO peripherals. I've got 2 I2C buses enabled. I've got the CAN enabled, so that's obviously going to go to my CAN connector. The I2C, probably the accelerometer is on there, I'd guess, and definitely some other peripherals if you've got 2 of them. We've got 2 UARTs enabled. We've got a GPIO enabled, probably to drive the LED to receive the input from the push button, the user push button. We've got an SD IO for the SD card. We've got USB for the USB port, and we got Ethernet. We've got a gigabit Ethernet MAC for the gigabit Ethernet PHY and RJ45 connector. So I noticed there are 2 UARTs on here enabled, so I know one of them is going to be my USB UART, and that's what I'm going to want to use for my standard IO. in my SDK application. So I want to know actually which one is that going to be, because there's 2 enabled. So I don't know why there are 2 enabled, but I need to find out which one is actually connected to my USB UART, so that in my SDK application I can make sure that my standard I/O is configured to the right one. Let's click on this. So I've opened my UART configuration. I can see I've got, let's just make it easier here. So I've got UART 0 connected to MYO 10 and MYO 11, and I've got UART 1 connected to MYO 48 and 49. So which of these, I want to know which of these is connected to my USB UART. So I have, I'm going to have to look at the schematic for the Z-turn. So if you go onto the MYIR website, go to downloads, you can download the schematic here, Z-turn board schematic. You can download that there, which I've already done. So this is the schematic opened here. If I just scroll down the page, now I can find the MIO pins of the zinc device. So now what I want to do is look at where exactly my USB UART is connected to. If I go back to here, UART 0 is connected to MIO 10 and MIO 11. So I'll look for them here. I can see here they are, MIO 10 and MIO 11. Okay, and I've got them here, so I'll have to search for that if I want to know where they are. Let's just jump to the other ones. So the other UART 1 is connected to MIO 48 and MIO 49. So if I look for those, maybe I'll just get a quicker answer. So here they are, MIO 48 and MIO 49, and I can see by the net name that they are connected to the USB UART. So what I just figured out here from the schematic is that my USB UART is actually connected to MIO 48 and 49, which is connected to the UART 1. So that's information I need to know when I get into the SDK, because I need to make sure my standard I/O is connected through to UART 1 and not UART 0. So I guess I can close this now, and all I have to do is hook up my clocks. I said I was going to use the 100 megahertz clock, which is the F clock 0. So I'm just connecting that clock through to the input clocks for my general purpose AXI master interface and my high performance slave AXI interface. So now that I've hooked up the clocks, the only other thing that I have to do is create a HDL wrapper. So I'll do that. Let Vivado manage wrapper and auto update. And when that's done, I can then go down to here and click generate bitstream. Okay, so now that the bitstream is complete, we can now export this project into the SDK. So I go File, Export, Export Hardware, include bitstream. Now I'll export it local to the project. So now I can launch the SDK by going File, Launch SDK. It was exported local and the workspace I want to be local. So I click OK, that runs the SDK. Okay, so my SDK is now open and there's nothing in there but one hardware platform specification that comes from my Vivado design. So the first thing that I want to do, because I'm actually wanting to boot off the SD card because I can't use the JTAG connector on this board, I'm going to have to create a Zinc first stage bootloader application. So I go New application project. I'll call it Zinc FSBL. Next, I just select the Zinc FSBL template, click Finish. So now that that's finished building, I'm going to add another application, but this time it'll be the Hello World application. And it's already selected, Hello World template, Finish. Now I'm going to have to modify the BSP settings to select the correct UART for the standard input-output. So I right click on my Hello World BSP and I click on Board Support Package Settings. And I click Standalone, and here I can see my standard in and standard out settings. They're set by default to PS7 UART 0, but as I showed you earlier, we need to actually set them to UART 1 because that's my USB UART and that's what I'm going to connect to. So I set them both to UART 1, click OK. And that's going to rebuild automatically the BSP and my Hello World application. So I just wait for that to finish. Okay, so now that that's finished, I want to now generate a boot.bin file for my SD card so I can boot off that. Now, in order to do that, I click on my application, I click Xilinx, and I click Create Boot Image. Now, in a recent version of the SDK, they added this feature where if you click on the application and you do that, it will automatically set up a .bif file with the right configuration so that you can generate your boot bin file without manually configuring everything. But basically, if you want to know how to configure it yourself, you have to set in these boot image partitions, the first one being the bootloader, which is the zinc fsbl.elf file. The second one's going to be a data file. It's going to be your bitstream, the .bit file, and the last one's going to be the .elf file of the actual application you want to run, which in our case is Hello World Elf. So I don't have to actually make any changes here. Just so you can see it completely. So I don't have to make any changes here, so I'm just going to click Create Image. And what that's done for me is it has created the boot bin file in this folder here. So we created our Vivado project here in Vivado 2017.3 Z-turn base. And the SDK, we made it local to the project, so that's why it's in Z-turn base.sdk. Hello World is the application name, and the SDK just created this folder boot image and has created our boot.bin file in there. So what I want to do now is copy this boot.bin file onto the SD card for my Z-turn, and I should be able to boot off it. So I've plugged my SD card into the PC. So now all I have to do is copy this file. So I'll say copy, and this is my SD card. I'll just paste the boot.bin into that, into the root directory of this SD card. So I'll close that and I will disconnect it. the first thing we want to do to the Echo server is modify the BSP so that it uses the right UART for the standard I/O. So I click on standalone, standard in and standard out. I want to set them to the UART 1 as I talked about earlier. Click OK. Now that's going to rebuild the BSP and the Echo server application. So if I go back to my SDK, the code I need to modify is in here. It's the lightweight IP source code. So I've got to go into contrib, ports, Xilinx, netif, and the file I need to modify is called xemac psif_firespeed. So I double click on that file. Now I'm going to go down through that file to a function that's called get marvel firespeed. Now this, if you read further on in the code, you'll find out that get marvel firespeed is the function that gets called to configure the PHY by default. So if it's not a recognized PHY, it will assume it's a marvel PHY and it will run this code to configure the PHY as if it were a marvel PHY. Now because we're not using a marvel PHY, the TX and RX clock delay settings are not actually getting implemented because it's not reading, it's not writing to the correct registers. So that's what actually we are going to do. So I'm just going to go and chuck it to the top of the file over here. You'll see the first two lines are for enabling the TX clock delay and the second two lines are for enabling the RX clock delay. So once that's made, I can just save that file. That will rebuild the BSP and my Echo server application. So now that that's done, I just need to generate my boot bin file. So again, I'll click on Echo server, Xilinx, create boot image. So I can see it's created for me the .bif file for me for the Echo server. If I want to make sure that it has everything in it, I'll just see here, it's got the Zinc FSBL, it's got my bitstream, and it's got the echo server.elf file in it. So I'll just click create image to generate the boot.bin file. That's created. Now all I have to do is copy it onto my SD card. So to copy it over, I go through to my folder that's in the Vivado folder, and then the .sdk folder, echo server, and boot image. So I go into that folder where my boot.bin is, I copy it, and then I move it over into my SD card. Then I close the SD card, I pull it out of my computer, and I plug it into the Z-turn. Now that I've got it plugged into the Z-turn, I can power up the Z-turn by plugging in the USB cable. I can see the LEDs have come on, so I know it's running. So now what I want to do is open up my terminal, which I had opened earlier. It's inactive, so I've got to restart it. So I restart my terminal. Now I'm going to rerun the Echo server by pressing the reset button on the Z-turn. I press reset. Now I can see the Echo server is running and the file is waiting to complete auto negotiation. So now I'm going to plug that here. I'm going to plug the Ethernet port into our router. So this cable here obviously goes through to our router and to our network. If I plug that in, the auto negotiation should complete, and it does. It negotiates a speed of 1 gigabit per second, and the DHCP server has given it an IP address, and the IP address is 192.168.220. So this board is running Echo server and it has been given an IP address. The only way I can check that now is to ping it or use Telnet to connect through to it. So let's try both of those. So I open up a command prompt, and the first thing I'm going to try is using ping 192.168.220, and as you can see, I'm getting replies from the board. So obviously my PC is connected to the same network. The other thing that I should be able to do is test it with Telnet. So if I type Telnet 192.168.220, and I have to specify Telnet, I have to specify the port number to Telnet, which is 7. As you can see in the comments over here, the Echo server is running on port 7, so I've got to type 7 here. So once I run that, now I should be able to type hello. This is the Echo server running. So as you can see, all the letters that I type are coming out doubled. That's because the Echo server is returning all the packets to me. So that looks like it's running, and I can exit.